Welcome to this project presentation. During those 2 minutes, Elisa, Kilian, and I will present our project, the Emmental project. So the core of our project consists of generating a cubic terrain with random 3D holes in it, smooth the surface to get a proper terrain, and render those cubes to get a good-looking visual. To do so, we have followed two main steps, 3D Perling noise and marching cube algorithm. First, the 3D Perling noise function. To apply the 3D Perling noise function, we took the Lab 7 skeleton, but we first subdivide our cube into smaller cubes and generate the faces using triangle meshes. We also updated the 2D Perling noise function to 3D in order to get a 3D noise map. Then for each cube, we look at the map, compare the noise value to a threshold, and draw the corresponding cube or not. This results in a voxel cube looking like the one on the right of your screen.
Next, we use marching cubes to get smooth surfaces. For each cube in a terrain, we check which cube vertices are above the noise threshold and which are under. This gives us an index, and we have a table for all the possibilities, and the value in the table gives us the actual vertices on which we should draw the triangles for the final mesh. Sometimes we need to draw faces with vertices in the middle of cube edges. In our implementation, we can only create faces from existing vertices, so we had to adapt our implementation for that. And at the end, we also had to add manually all the side surfaces of the cube. We also had time for some extensions. You can see here some of the things that we have done, and Elsa will present them more in details in the demo. Now let's go onto the demo.
So here we have the basic functions of rotating, zooming, and we added as well panning with the option of moving inside of the cube, as you can see it here. By pressing C, we can go to the preset view, and then we have all the sliders with the resolution to choose how smooth and how many vertices we have, scaling for the distance between these vertices, the noise to change the noise function, as well as the threshold, for the threshold. And by clicking on the checkbox, we can also choose to have a sphere inside instead of the cube to change it a bit.
Hello and welcome to the realistic burning building presentation by me, Jacob, Vincent and Nicholas. As you can see, the scene consists of a house exploding or catching on fire, as well as a planet rotating around this house, also exploding or catching on fire. The explosion effect is done with sprites of 48 different frames of animation, as you can see here. The position of the explosion as well as the animation frame is determined by the simulation. A random velocity and lifetime for the explosion is generated every explosion cycle. And the position is determined by a simple starting point plus velocity times time function. For every call to draw on these sprites, we check if the lifetime is expired, and if so, we generate a new lifetime.
Hi there, this is Group 4, and this is our project, Ray Marching Fractals. The scene is only rendered using 2 triangles. All of the visuals you see are computed inside of a fragment shader. We use a technique called ray marching, which allows us to implement these nice reflections and shadows using the same principles we saw for ray tracing in our class. To render fractals, we use complex space folding functions, which allows us to create these intricate patterns in our shapes. For more information, you'll probably want to read our report, so for now, I'll just leave you with the visuals.
For the sun surface shader, we used a combination of differently scaled gradient noise that is used to interpolate between the bright and dark color to create this sunspot and rotation effect. For both the sun glow and the nebula, we used billboard particles that are two-dimensional and always face the camera. In case of the sun, the particles are initialized with a random color that is interpolated between 2 specified colors, a random limited rotation speed and a random limited size. The particles used for the nebula are additionally given a random radial speed so that they expand over time.
We set up the camera path using a Bezier curve controlled through anchor points. We also created trigger boxes along the path to change camera target, camera speed, and trigger events like the supernova explosion. We created an L-system framework to generate arbitrary systems given an axiom and a set of rules, with or without randomization. We used these to give some volume and structure to the nebula. We shaded the meshes with a moving texture to make it more lively, and we added the vertex noise displacement shader to give it a more natural feel, as you can see here.
So I'm going to talk to you about our project, which was to automatically generate buildings using an algorithm. And you can see one of the results on the right. First, we implemented a rotate, translate, scale view with the mouse and keyboard to move around our buildings. Then we created a set of tiles with Magica Voxel, which is a software to create 3D cubes. Then we implemented the wave function collapse algorithm that I'm going to talk to you in a second. We also added a day-night cycle and also a Bezier curve that we use to reset our camera to get a smooth transition. So for the wave function collapse algorithm, first for each kind of tile, we have to declare a set of adjacency constraints. Then for all of the possible cell, we need to list all the possible tiles. Then we pick the cell with the least possibilities, and we pick one of the possible tiles at random, and we propagate the choice to the neighbors depending on the adjacency constraint. If the neighbor's possible list was modified, we propagate further, and we repeat until no cell have more than one possible tiles.
The goal of our project is to generate an infinite map using 3D Perlin noise and the marching cube algorithm. The main purpose of this algorithm is to approximate shapes. Here is an example in 2D. It basically creates a grid around the shape, computes the intersection points between the shape and the grid, and binds these points together. We implemented a 3D version of the algorithm. Here is an example with a sphere. To generate our terrain, we divided it into small cubes and used the 3D noise function to give values for each corner of our cubes to tell how much we are inside or outside the surface at these points. From there, we can generate the triangles that bind the faces to create our mesh using a lookup table. The second picture shows some floating islands created with the marching cube algorithm. A second technical aspect was the generation of an infinite map. To implement it, we decided to use 9 chunks to generate our map. Whenever the camera is moving, we delete the 3 chunks that are in the opposite direction and compute the 3 new chunks. Like that, we always have 9 chunks in front of the camera and it looks infinite. Here is a preview of our project.
We carefully handcrafted our lighthouse and island in Blender. The custom UV mapping handles the different materials texturing that we have. That is, rock, concrete, metal, and glass. The sea is first initialized with a purling FBM noise. This allows us to have a believable wave appearance. Each vertex is connected to its neighbors by springs, and we can update those with a simple spring equation. To replicate the wave crashing against object, we define a collision map that we store in a texture. The collision map is initialized once by fixing the water level at the space occupied by the object to the sea level. The wave update is done differently there. The incoming force is damped and reflected. To finalize our scene, we added two different lights, one for the moon and the sun, and one for the lighthouse.
To choose which tiles go where, we used a wave collapse function. To understand how this works, you can picture a 9x9 Sudoku. At first, all cells can have any value from 1 through 9. But say you want this particular cell to have value 5. Because of Sudoku constraints, this will remove the number 5 from the possibilities of certain cells. Similarly, if we want to put 2 here, and so on and so forth. Our wave collapse works the same way, first assigning all tiles to all cells, and then removing them as we go and constraints start appearing.
Elon Musk sent a Tesla to space, and after years of loneliness, it finally found a home. It now lies peacefully on a new planet, far away from here. Sadly, the aliens tried to drive it and broke the wheel. Now the car can only go straight. Have fun visiting this planet aboard this car and meeting its people, its ecosystem, and even a satellite that crashed here.
Hello everyone, we are going to present our project, which was to implement the wave function collapse algorithm. The problem this algorithm solves is a constraints problem. The basic principle is that we want to fill a grid of cells where each cell can initially be any tile or pattern, and we want to find a combination that respects a given list of constraints. The algorithm proceeds iteratively, where each step it collapses a cell and assigns it to a given tile or pattern, and then propagates the result to the neighboring cells, which update the remaining possible tiles to still satisfy the constraints. There are two major input models for this algorithm. The first one is the overlapping model, where the input is a bitmap from which patterns and constraints based on the colors are automatically extracted and then fed to the algorithm. It is so called because the patterns can overlap with each other. The second model is the tile model, where the tiles and constraints are predefined and the algorithm just places them adjacently. So here you can see some examples of the overlapping model, where the initial pattern was on the left and the right was what the result produced by the algorithm. And now you're going to have a live demo.
So here is an instance of the algorithm that construct the final mesh with 3D tiles going on the ground. We implemented the Fong lightning model and the shadows to bring some reality to the scene. Two lights are orbiting around the scene with different colors and intensities. They represent the sun and moon cycle. Some tiles are also fixed light emitters. For instance, you can find a torch, campfires, or light towers. Regarding the camera controls, we can zoom in and out with the mouse wheel, as well as rotate around the scene with the mouse. We can shift the view with W, A, D, S, pause the simulation with P, and get back to the preset view with C.
Also, the scene is always randomly generated by the algorithm. Finally, here is an example when we use tiles that can go up and down, allowing for scenes with more 3D in it.
Our project consists in the procedural generation of nice-looking 3D landscapes. The mesh creation is done with the marching cube algorithm, and the color of each vertex depends on its size. A system of chunks and rendering distance gives the illusion of an endless terrain. We show the nearest ones and hide the furthest ones. To enhance our project, we added the following features. We generated freeze thanks to stochastic 3D L systems, and we implemented a day-night cycle. Finally, we generated water planes meshes when the depth was too low.
Hi, in this video we will demonstrate 3 separate non-photorealistic rendering techniques we implemented as part of our computer graphics project. First, we implemented a cell shading shader which produces a cartoon-like effect. This is done by separating brightness values into ranges and applying the same brightness to the whole range. As the separation can look a little rough, we made our shader be able to smooth out the transitions between brightness values and choose the number of ranges to apply. We also implemented an outline. This is calculated by coloring in the surfaces where the normal is nearly perpendicular to the viewing vector. Our second shader uses tonal art mapping, which aims to reproduce pencil hatched lighting. This is done by applying different hatch textures depending on the brightness and smoothly mixing them. We also made an option to choose the number of textures to apply. One important thing to note is that the textures need to overlap. This makes the transitions between them invisible. The last technique we implemented is half-toning. This represents colors using cyan, magenta, yellow and black dots. This is done by making a grid of dots for each color, where the radius of the dot scales with the amount of that color on the Phong shaded surface. We make sure to rotate the grids different amounts so the dots fill out the texture. We also made it possible to choose the amount of dots displayed. Our implementation has a few problems, however. First, there's a lot of aliasing that occurs when the dots are close together. We have some anti-aliasing in our code, but it doesn't address all issues. The second problem is that different textures need different amount of dots, or they need to be looked at different distances to look right. Thanks for watching our presentation.
Welcome to the presentation of our group project. This is what regular Minecraft looks like, and this is what Minecraft can look like. For our project, we decided to implement our own Minecraft shader pack. This shader pack features soft shadows, bloom, ambient occlusion, wavy water, and screen space reflections. We'll calculate a shadow using a depth map as well as a shadow map. We'll reconstruct the fragment position from the depth map and the closest point to the sun between fragment and sun using the shadow map. Then, as usual, if the fragment position is behind the closest point to the sun, the fragment is in shadow. The screen space reflection for the water works by reflecting the screen image onto itself using only itself. By reflecting your screen onto itself, you can create the illusion of reflection. In one of the final full screen passes, pixels above a certain brightness threshold are collected. We then apply Gaussian blur to spread out the pixels. We add the result of the blur to the fragment color, and then we have this nice little blur effect. We spent quite a lot of time trying to understand the Minecraft shading pipeline, but we got some results in the end, and here they are.
Hello! We created a simulation of a system of particles. We created simulation of fire and smoke using billboard sprites. We also used noise for texture, noise such as FBM or turbulence. We also included possibilities of user interaction.
From our previous lab base, we implemented a simulation of particle systems. So as we said, we made a fire and smoke simulation using small particles that are always facing the camera.
You can interact with the project by stopping the simulation time, hiding one of the particle system, or even moving them using the arrow keys. If you want another ambience, you can always change the fire color. We will show you some example now.
Introduction to Computer Graphics Swarm project. What is all about? We have implemented a simulated 3D world where agents fly in a swarm formation. Each of them are autonomous and act locally based on simple rules. The combination of these rules make a coherent ensemble which is the swarm. Some of them are based on Boyd's rules and they are configurable. Everything else in the simulation, meshes apart, is randomly generated. We can create different possible behavior, such as a flock of birds, or a swarm of insects. Thanks for watching.
Today we're introducing our project, Particle of Fire and Smoke, and it was done in collaboration between Antoine Deniker, Belton Michel, and myself, Alexandre de Matos. Concerning the features of our project, so we have a particle emitter that was the main part of it. And concerning these particles, so we represented them as sprites, and they are animated over time. So concerning their appearance, so their appearance evolves with time. They also move in space in different directions. They are able to collide against different obstacles, and mainly we have multiple types of particles. So fire, smoke. We were also able to sort the particles by depth to avoid transparency between particles and to actually generate their position on the shader. So we have an instance renderer. We were also able to implement cylinder collision using ray tracing technology. And we have multiple shaders for the different types of particles, so for the smoke and for the fire. And finally, what makes the shots that you will see after this presentation nice were implemented using the Bezier curve that we put on the project.
Group 31 and our project is called 3D Collision Simulator. We first want to very briefly talk about some of the technicalities of the project and end this video with a demonstration. In this project, collisions of 3D spheres within themselves and with the static objects found in the scene are simulated. We first created a static scene using Blender. The scene consists of few obstacles of box-like meshes and walls with which all the spheres can collide. Each sphere's velocity, position, and other characteristic features are stored as ball class objects, which we defined for practical reasons. And the main focus of the project was to build an acceleration structure for collision detection. We implemented an octree structure for recursive space partitioning purposes in order to accelerate the rendering time. And now we want to show a demonstration of the project and explain the scene a bit further. As mentioned before, the scene consists of walls and 3 box-like obstacles, and currently there are 30 spheres which can be changed, and each of the spheres have a predetermined initial position and initial random velocity and color, and in each run these velocities and colors are changed. The camera has 2 modes. When button B is pressed, the camera moves along a smooth path calculated using Bezier curves. And when the button C is pressed, the camera can again be controlled by the mouse to zoom or drag or rotate. And again, using button C presets the view. Let's use the Bezier camera for now. All the collisions we have in this system are elastic collisions, which means there is no friction in any of the surfaces. Thus, the energy of the system is preserved and shown in the debug text to check whether there are any kind of errors or not. And this concludes our demonstration. Thank you for listening to us.
Hello and welcome to our computer graphics project, Interactive Wave Collapse. So first of all, the wave collapse algorithm was made by first generating a random tile at a random spot to initialize it. Then we generate neighboring tiles while respecting the constraints and keep doing that until the chunks is filled with tiles. So the constraints are numbers, and if 2 tiles have sides that match in constraints, they can be placed next to each other. And some rotation problems are avoided using arrays. Infinite scrolling is done using chunk, regenerating them as we get close to them and only displaying close chunks to avoid lag. Then free camera movement is done using a rotating camera around the origin and then translating it to the correct position to create a smooth movement. And then water perturbation uses Perlin noise to alter the height of the water and simulate waves. As you can see, we are able to generate entire chunks that are consistent regarding the constraints that have been set by ourselves. However, as you can see here, the chunks we are generating 9 chunks, but for infinite scrolling, we are unable to properly respect the constraints at the chunks border, and this is because the approach that we initially chose turned out to be not very well adapted for the infinite scrolling, so we would have had to completely change our approach, which would have taken too much time given the time that we have left. As we can see, we can also move around freely using the keyboard and mouse. We are only displaying chunks that are close to us, the 9 chunks that are closest to us to avoid lag, but we are generating them on the fly as we are moving around in the scene. And we can also see how the Perlin noise affects the water, especially here, for example, in this kind of sea chunk, sea area where we can distinctively see waves.